Hello everyone, it's Zenith20 here again, and this video will be making a randomized maze using DFS. Maze generation is an interesting algorithmic problem where the goal is to create a maze-like structure with multiple paths and dead ends. Luckily, one of the simplest and most effective algorithms for maze generation is randomized depth first search, or DFS. In this video, you'll learn how DFS works, how to utilize it in randomized maze generation, and also visualize it using the canvas and the Canvas API step by step. But before we begin into that, let's have a basic visualization of how exactly depth first search works in its core nature. Depth first search is an algorithm for traversing or for searching tree or graph-like data structures. The tree or graph-like data structures are basically made of individual cells, or in other words, nodes. Those nodes have neighbors, and those neighbors have the further neighbors, which then eventually connect to each other, forming a graph-like structure. Hence, for such graph-like datasets, we use depth-first search. The depth-first search always starts at a root node, and that root node can be any starting node or any arbitrary node, which we could choose as a starting node, and then it explores as far as possible along each branch. So it starts at the topmost branch, and then it goes as much deep as it can into the graph. So in this case, it goes branch by branch and not level by level. So it starts from the topmost node, and then it goes to the deepest node in the branch. And then after that, it needs to do backtracking to move out of that branch because it cannot go furthermore into that branch. For that, we usually use a stack. And this is the extra memory which stores all of the nodes that we have visited. And then from that, we backtrack when we don't have any more further neighbors to traverse. We can begin with a basic graph over here where we have the nodes A, B, C, D, E, F, G, H. We can say the root node or the start node to be the A node. We could take any other node as well, but in this scenario, let's just stick to the A node as the start node. Now, of course, we're going to show color highlighting over here. So we'll have the orange color for indicating the current node which we're working on, and all the green colors will show the unvisited nodes. And you can see that currently all of the nodes are unvisited. And for all of the visited nodes, we'll have the blue color. We'll also be utilizing a stack to visualize how exactly is the program working in the background to turn all of the nodes into stacks. So first of all, we start at the root node, and the root node is A over here. So we start at the root node and we mark it as visited and we push it to the stack. Next, we add one of its neighbors, and we can choose a random neighbor. In this case, we choose the B node as the neighbor, and we also make it the visited node, and then we push it into the stack. And you can see how the A node has moved downwards in the stack, whereas the B has come to the top of it. Again, we mark the B node as visited, and then we visit the C node. So we're going one of the nodes step by step deeper into the branch. So in this case, we also add that C node to the stack, and we mark that as visited. Now, in this case, we have reached the end of our graph or the end of our tree. From here, we need to backtrack. Therefore, we pop one of the nodes, or we remove one of the topmost nodes from our stack, and then we are going to traverse backwards from that node. Now, on the top of our stack, we have the B node, and we have backtracked to that B node essentially. And that's where our current node is. Again, we're going to remove that B node because there are no more further nodes which we can explore from that B node. And we get back to the A node. So you can notice how every time in backtracking, whenever we'll be backtracking from any branch, the starting node will always be the root node. Again, we find an unvisited node and we put that to the stack. And now the stack has that visited node. And for that visited node, we again choose a random node. And then we go to that random node and we also mark that as visited. Along that, it's the current node, and that's also pushed to the stack. Then we go further deep down into the deepest node in the branch, which is the F node. And again, that F node is pushed into the stack and marked as visited. Now, the same scenario over here, we cannot traverse any further deep down from this node. Therefore, we start backtracking by removing one of the nodes. When we remove one of the nodes from the stack, we are left with the previous node, or the parent node in this case, which is the E node. Again, the E node does not have any unvisited neighbors to offer to us. Therefore, we backtrack from here, and now we're here at the D node. The D node is not the root node, but it does not mean that we cannot traverse further along from here. So in this case, if we look at the graph, we still have the G node after the D node. So the D node gives us the G node as the unvisited neighbor, and we push that to the stack, essentially completing the entire traversal of the graph. From here, we can again start backtracking to remove off from the stack. The G node is marked as visited, and then we pop off the G node and we go back to the D node. And from the D node, we go back to the A node as the stack is being cleared. And then from the A node, we simply complete the execution of the DFS and return from the DFS execution, thus completing the entire traversal of the graph. Now let's move on to the actual maze generation with HTML, CSS, and JavaScript. All right, now to leverage this depth-first search algorithm to generate a random maze, we're going to be utilizing the canvas in the HTML so that we can render the actual maze, nothing else than that, and we'll be just connecting a script and the style sheet. There is not much styles, of course, this time. We're just having on the background of a dark color, and then we'll have just display effects, and we'll align everything to the center so that at least we can have a basic styling on the website. So currently, this is the state of the website right now. Otherwise, the index.js is completely empty. So let's get into it. We'll first of all take our canvas by using document.query selector canvas. Next, I'm going to define the context. Let C is equals to canvas.getContext 2D. So what basically this line is doing is that it's assigning the context of the canvas. The canvas can either have a 2D context if you're making 2D graphics, or it can have a 3D context if you're animating 3D objects. And why am I using C over here is that because we'll be using this context variable many times. Therefore, it will be a tedious thing to rewrite the whole context variable again and again. You can keep the full context word, or you could keep the small c letter. It's up to you which one is easier for you. Next, I'm going to take an object-oriented approach for creating this maze by creating two classes. These classes will act as the blueprint from which we'll instantiate our maze, and we'll have the individual cells inside the maze, which will be basically individual nodes as previously discussed. So first of all, let us start with a class maze. It's going to have a constructor which will take in some parameters. Now our maze will have a size, and it will have rows and columns. For now, we'll assume that every maze will be a square shape. So therefore, we don't need to go into the complexity of defining separate heights and separate widths. Now, these are the parameters. We want to set the properties of this maze object. So for that, we'll do this dot size is equals to size. This dot rows is equals to rows. And this dot columns, or we can keep it short for cols, equals to columns. Now we have set the properties for our maze. Now we're going to define two extra properties. First will be the grid, and this will be the actual array, two-dimensional array, which will be storing all of our cells, and we'll be having the stack as we had previously discussed, so that we can track which cells we're visiting, so that we can also further backtrack it when we don't have any further neighbors for the cells to visit. So the stack will also be a simple array. All right. Next, we'll define a setup method. And in the setup method, we'll be building our actual grid. But before we do that, let's construct the actual cell which will go into the maze. So the maze will also have a constructor. It will have size, or in fact, it will have a parent size, parent grid, rows, columns, or we can just keep cols. Okay. Now we're going to set all of the properties. So this dot parent size equals to parent size. This dot parent grid equals to parent grid. This dot rows equals to rows, and this dot columns equals to columns. Now, two additional parameters we need to introduce, which is the row num and the column num. This dot row num is equals to row num. This dot column num is equals to the column number. All right, that's the basic information for the cell. Next, we're going to define some additional properties from ourselves and not from the parameters. So we have the parent size and we have the rows. And as I had already discussed that our maze will always be a square shape, we can calculate or we can pre-calculate the size of each cell by taking the parent size, this dot parent size, or we can just take the parent size and we can divide it with the rows or the columns. It does not matter because in this case, our maze will always be the square shape. Next, we are going to define this dot walls. Each cell will be consisting of 4 walls, and that is what will be defining our cell. Whenever our maze generator will go from one cell to another cell, it will be breaking walls in between and basically carving its way and creating the pathways inside the whole maze. Therefore, we'll need to show the walls in some manner. So for that, we'll create an object which will contain the walls. It will contain 4 properties. Top wall is true. And we can copy this over and change it to top wall, bottom wall, left wall, and right wall. Okay, next we need to define a very important property. And this property is this dot visited. Basically, whenever our maze generator will be visiting each and every cell, it is important that we mark those cells as visited. Otherwise, our maze generator would end up revisiting those cells and will be stuck in an infinite loop. So we'll make this dot visited equals to false. And that should be it for the basic properties of the cell. All right. So now back in the setup method in the maze, we'll have 2 for loops. For let r is equals to 0, r is lesser than rows, r plus plus. This will be the loop for the rows. And we'll copy and paste this inside to create a nested for loop. And the second loop will be for the columns. All right. Make sure this is a semicolon. Next, in the first outer for loop, we're going to define let row or the current row equals to an array. And inside, in the most inner for loop, we're going to define our cell. Let cell is equals to new instance of the cell class. And this will pass in the parent size or the size, in this case, the size, the parent grid, which is this grid property over here, and the rows and the columns. Make sure the rows is prefixed with rows. Each of these properties should be prefixed with this, otherwise we'll end up with many errors. This dot rows, this dot columns. Next, we need to define the row number. We can pass in the r variable of our loop and column number, which will be the c variable of our loop. We are going to push this into our row dot push cell. And we are going to push the entire row into our grid in the outer loop. This dot grid dot push row. All right, that's the basic setup. On the top over here, I'm going to define a current variable which will hold the reference to our current cell which is being visited. This will be used later on in the DFS maze generation. So for right now, we can set our current to grid 0, 0. In this case, the starting point will always be the top left corner. You can modify it as much as you want later on, but for now, we'll keep the starting point of our maze generation from the top left corner. We can now check if this all is working by instantiating a new maze. Let maze is equals to new maze. We're gonna give in the size and the rows 10 and columns 10. And we are going to call maze dot setup, and we're going to console.log our mazes grid to check if everything's hooked up correctly. So we have the grid over here, and you can see it's a two-dimensional array as we had made it. Two-dimensional array with each of the rows containing cells. Each of the cells are containing the parent size, the column number, columns, and the rows along with the row number. We can take the last row, check the last column and the row num, and we have the right row num and column num along with the parent size. All right. We maybe have passed in the wrong variable here. All right. Parent size must not be an array. Okay. This dot size. What are we passing wrong? Parent size. And then parent grid. Okay. In the class cell line 30, we should set the parent grid property over here. So if anybody would have copied this to parent.size over here, we're basically setting the parent.size property 2 times. We need to set the parent grid to the parent grid parameter, which we had sent over here. And now if we check our array, we should have the correct parent size of 500 and the parent grid with the right property value. All of them are unvisited for now. Okay, so now we need to draw the actual canvas. So for that, we'll have a draw method in our maze, and we're going to define the canvas's width as the size and canvas's height as the size. Now, why am I setting the canvas's width and height in the index.js? Well, this is because if you will try to set the height and the width of the canvas in the CSS, what it will do is that it will try scaling the canvas. And this might result in some blurry drawings whenever you try to draw on the canvas. So if you want crisp and clear drawings and the corner of the items which you'll draw on the canvas, you need to set the canvas's width and height from the JavaScript. Both of them will be set to size, and we'll be assuming that the maze will always be a square. Next, we are going to give our canvas a background. Canvas.style.background is equals to, let's give it a light color, hashtag 121212. All right. Or maybe let's give it black for now. Okay. We still can't say anything because we haven't called this method. So we're after we've set up the maze, we are going to draw our maze. Make sure that you're drawing the maze after that you have set up the maze. And there we go. We have our maze in the center. Pretty bland right now. Okay. Next, in the draw method, we are going to loop over our grid. Grid dot for each row. You need to remember that our grid is a two-dimensional array. Therefore, we'll have to create 2 for loops. So for each row in the grid, and then for each row, we'll have access to the cell. And in this, we're going to do cell.show. Now this cell.show will basically draw out all of the walls according to the walls property, which we have set over here in the cell class. So let's go ahead and create the show property. The show method will consist of one function call. That will be this dot drawWalls. Okay, so this dot drawWalls will be a bit lengthy function because we'll be drawing out all of the 4 walls. The actual drawing of the walls will be handled by this function. So from where we'll start is that we'll define a from x, that will be 0, and a from y, that will also be 0. We're going to copy that, and we're going to have from x and from y, but this time they will be 2x and 2y. because we'll be drawing out each of the walls as an individual line. Okay, so we're going to go over, first of all, the top wall. We're going to check if walls dot top wall. So we're saying if the top wall exists, if the top wall is set to true, we are going to set our from x to size, or in fact, column num multiply with size. And we're going to set our from y to this dot column num multiply by size. We are setting it to column num multiply by size because basically each of the sizes will be multiplied as column num, so it will be moving forward. You need to also remember in this case that our column num translates to the x coordinate, whereas our row num translates to the y coordinate over here. So we'll have the from x and from y as the top left part. Always the line will begin at the top left part of the canvas. So we need to consider the line to start at the top left side because it does not start from any center point. It starts from the top left side. Okay, so we have the from x and from y. Next, we're going to have 2x. So this is the top wall. So for the top wall, we're going to start from the top left corner and we want to go to the top right corner. So for going to the top right corner, we just need to modify the from x. So basically, we'll move from x plus size. So we're saying that we're starting from this top left corner. If we add the size of the cell into this from x, we're essentially offsetting towards the top right. Now 2y will be from y. There will be no change to this variable because we're just setting the top wall. Next, I'm going to define a small function over here, which will be drawLine, because we'll be repeatedly calling these statements. So it's better if we encapsulate it in a function. Over here is where we'll be using our context variable, which we defined above. So this is where the canvas's API comes. So we're going to say context or c dot begin path. That will initiate the path for us. And then we're going to say c dot move to. This will move to the starting point of the line. So in this case, we'll have the from x and from y. drawLine will take in parameters from x, from y, to x, and to y. So we're going to move from x and from y. And then we are going to call line 2. So this is saying that where is the ending point of the path or the single line which we're drawing. So line 2 will be 2x and 2y. Now that we have set the starting and the ending point for our line, we're going to call the stroke method. And this will be the actual thing which will be drawing the line. So it's like that we're deciding the starting point and the ending point for our line. And then we're pressing the pen down to actually draw the line. So that will be the c dot stroke. But before that, let's also define the stroke style, because currently there is no stroke style for the line. So stroke style is basically the color. What will be the color of the line? In this case, we'll set it to white. And we can set the line width. This will be the width of your line. So the line width, we can set it to 2 for now. And there we go. We have a drawLine function, which we can call here in drawWalls. So we have set all of the parameters. Now we can just call from x, from y, to x, to y. And now if we go check, all of our variables are not having the correct order. Let us see what's the problem here. Okay. Our walls are not rendered correctly. So from x, from y. We're setting the top wall. So from x is the column num, from, oh, okay. So from y should be row num. So the from y should be the row num. Over here, the row num is our y coordinate. And now if we check, we have all of the top walls rendered. This is the top wall for the first row, second row, third row, fourth row, and so on. Now we can essentially copy this and check for the bottom wall. So if the bottom wall exists or if the bottom wall is true, we will essentially start from the bottom left corner and we'll go to the bottom right corner. It's basically the vice versa of the top wall. So in this case, we'll have the from X, the same coordinate, from Y will change. So we can encapsulate this in brackets and add the size to it to move downwards or offset our drawing line, the equal amount of size of our cell. So from Y will start from the bottom left corner and our 2Y will shift over here. 2X will not shift at all. So 2Y will be from Y plus size. Now if we check, we also have the bottom walls, except that, no, these are not the bottom wall. Okay, so from X, we start from the bottom. Okay. And then from Y, we are starting from this dot row num bottom corner. 2X is from X. Okay, no. 2Y should not be modified. 2X must be modified. 2Y should remain same. We're still on the same y-axis. Okay, now we have the bottom walls rendered because this will be acting as the bottom walls. Okay, now we can copy this again and set our left wall for each cell. So for the left wall, we will be having for the left wall, we want to start from the top left corner of the cell and we want to go to the bottom left corner of the cell. So you can see in this case, our y component or the y coordinate is shifting. So from X will be remaining same. From Y, we'll start from the top left and we'll pull this. 2X will remain same and 2Y will be from Y plus the actual size of the cell. And now we have the left side of each of the cells rendered. We can now copy this one last time to check for the right wall. For the right wall, we'll be starting at the top right corner and we'll be going to the bottom right corner. So that will be from X, this dot column num multiplied by size plus the actual size of set. And from Y will remain the top. 2X will remain the same as from X. The Y component will only change. So 2Y is from Y plus the actual size. And there we go. These are all of our cells rendered out, or essentially the walls of our all cells rendered out. Okay. So now our draw function is completely working. We are now going to call in the draw function request animation frame. What request animation frame is doing is that it essentially calls your draw function again and again and again at the fastest rate that your computer can basically run the frames. So for that, we're going to just request the animation frame so that it can call our function again and again. And we're going to pass into it our draw method, this.draw. So what this call over here does is that it essentially creates a loop for our animation. When we'll be updating each of the cells and when we'll be showing when the walls are breaking, we want to visualize that, the DFS maze generation. Therefore, we're going to call that in our draw function and we want that to be animated. Okay, so we have drawn the walls. We are now going to add another function for removing the walls, or maybe we can first of all set the DFS. Okay, so we can go to our maze and we can define another method, which is DFS Maze. And this will be the actual function which will be creating our maze. So the DFS Maze, as mentioned, will first of all take the current cell and will mark it as visited. Then it's going to request the neighbor for that current cell. And there is no system in which we have defined how we'll get the neighbor. So let's go into the cell and first of all, define a property in the constructor part of the cell, which will be this dot neighbors. The neighbors will be an empty array and the neighbors will basically contain all of the surrounding cells of the individual cell. So if you think about it, the neighbors for this cell is this bottom cell and this right cell, but not the left or the top cell because that's outside the grid. But this cell over here has 4 neighbors, one to the left, top, right, and bottom. We're not considering the diagonals one over here. And another thing is that we're only going to select those neighbors which have not been visited. So basically, we want to select those unvisited neighboring cells. So for that, we'll have setNeighbors function, first of all. The setNeighbors function will be inside the cell class. And the setNeighbors is, first of all, we're going to get each and every neighbor. So let's think about it. How will the left neighbor be for each of the cells? So the left neighbor will only be available if our column num, which is the x component over here, if our column num is not equals to 0. Because basically the left cell is the current cell minus itself. So if we go backwards, we'll find the left cell. But if in this case, we're already on the topmost cell and we try to go backwards, it will give us an error because there is no cell over here. So we're checking that if our column num is not equals to 0, which basically means that we're negating all of these cells because all of these cells are having the column num of 0. So we're saying if this column num is not equals to 0, then we're going to start a ternary operator over here. We're going to say parent grid, and we're going to put into it column num, or let's just set the column num. First of all, let x is equals to column num and let y is equals to row num to shorten stuff up. So we're going to go first of all with parent grid y, because first of all we'll be accessing the individual row. So first of all, it will be the y component. So y will remain the same, but then we're going to access each and every cell in the row. So we want to access the backwards cell. So we're going to do x minus 1. And that will give us access to it will give access to the cell which is behind us. And otherwise, we'll put colon. Otherwise, if the column num is equals to 0, we're going to return undefined because there is no cell beyond that. You can do the same thing for the right. Okay. Where did the modification happen? Okay. We didn't have to modify that. So we're going to set the right cell, and we're going to this time check if column num is not equals to the total number of columns. So we are saying that if any of these cells are being checked, don't give them the right cell because there is no right cell existing for them. And all of these cells have their column num equals to the total number of the columns. So in this case, the total number of columns according to the array is 9. And all of these are having 9 column num. And if we'll try to exceed that in by any manner, it will then give us this cell. Obviously, this cell is not the neighbor of this cell over here. It's on the next row. Okay. So the right neighbor will be if this dot column num is not equals to columns, we're just going to do x plus 1, saying that this will be the next cell beyond us, and otherwise we're going to return undefined. And next we can copy this and put top neighbor. And for the top neighbor, we're going to check row num. If row num is not equals to 0, so the same case over here, we'll not be checking for these cells because these are all having a row num of 0. If this row num is not equals to 0, then we're going to do y minus 1. So we're going to check above ourselves. Otherwise, we'll return undefined. Next, we're going to do the bottom. So if this dot row num is not equals to rows, so basically we'll not be checking for this row over here because if you go any more beyond that, there will be no cell. If this dot row num is not equals to rows, then y plus 1 with the same x coordinate, otherwise undefined. Okay. Now we're going to check individually. So if left neighbor exists and not left dot visited. So we're saying that, okay, we have the left neighbor, but is it visited? So if it's not visited, we're going to push it into the neighbors array. So we are saying that we are having now one valid neighbor, which is yet not visited. And we can copy this over 4 times and change these to the corresponding neighbors. Left, right, top and bottom. Okay, so we'll push these all into the neighbors. And before we push it into the neighbors, make sure that we clear the neighbors every time. Otherwise, it will keep on pushing the new and new neighbors again and again. Okay, now that's the setNeighbors function done. We are now going to use a random neighbor because our maze generation is based on randomized depth first search. It is like depth first search, except that we're going for random neighbors. So in this case, we are saying that, okay, we start from this cell, choose a random neighbor, suppose this neighbor. And then for this cell, choose another random neighbor, maybe this cell, and then choose another neighbor for this cell. So maybe downwards and so on. It will keep on going and going and going, choosing a random neighbor and creating one of the paths into the maze. Therefore, it is called randomized depth first search for this maze generation. So therefore, we're going to now create a function getRandNeighbor, which is a very easy function to implement because we already have the neighbors. First of all, we're going to call the setNeighbors always so that we can have the available neighbors to us which are yet not visited. Then we're going to have a random index, which will be math.floor, so that it will be a whole number, and math.random multiply with the neighbors.length. Now, before that, we can check another condition over here because it might be sometimes there that if the neighbor's length is not greater than 0, then we just want to return undefined, basically saying that we don't have any more neighbors left. And this will be the part where we'll be doing the backtracking. As mentioned before, if there won't be any more neighbors left, we'll be backtracking to the previous parent nodes. So if our neighbor's length is equal to 0, we'll just return undefined. Otherwise, we're going to get a random index and we're going to return neighbors rand. This will get us a random neighbor every time. Now we can go back into our DFS maze and we can define let next is equals to get rand neighbor for the current dot get random neighbor. And in that, we're going to check if next. So we're saying that, okay, so if we have the next cell available now, so we're going to push in our stack dot push the current cell as we had previously discussed. We're going to push the current cell into the stack and we're going to remove the walls. Current dot remove walls between our current cell and our next cell. Current and next. And we are going to define this function over here. So we can go back to the cell and we can define our removeWall method over here, which will take in cell 1 and cell 2. So first of all, we want to get the difference between the x coordinate and the y coordinate so that we can understand which two cells are going to have their walls removed. So in this case, if you're trying to remove the wall between this and this cell, it will be this part over here. And you need to notice over here that this is not one single wall, but this is the combination of the right wall of this cell and the left wall of this cell. They both are very close together, so it looks like it's one wall. Otherwise, there are two walls present over here. Same case will be for the top walls and the bottom walls. So let's do that. So first of all, we'll find the difference, which will be x diff. X diff will be cell 1 dot column num minus cell 2 dot column num. Okay. Or in fact, let's do it the other way. We're going to check from the greater one, cell 2 dot column num minus cell 1 dot column num. And we're going to check if the x diff is equals to 1, which basically means that our column or our row or actually our cell is the front one, because if we subtract the column num of this cell from this cell, and if it's 1, that means that this cell is after this cell. So we're basically checking for our right neighbor in this case, or the right cell. So x diff of +1 equals to, that means that we are checking for the right cell. So we'll have the walls of those removed. And for that, we're going to do, for that, we know that cell1 dot walls dot right wall equals to false. And as I mentioned before, there are two walls there. So we're going to also remove the left wall of cell 2. Left wall equals to false. All right. Now we're going to add another condition. It will be an else. Else if xdiff is equals to -1, which in this case means that our cell over here is behind the actual cell. So suppose this is our target cell here, but our actual cell is behind here, which means we'll have to separate the backwards wall or the wall which is behind. And for that case, we'll just swap over their walls. So we'll be removing the right wall for the cell 2 and the left wall for the cell 1. We can now copy this over and do the same for the y-axis, where we'll check the difference in the y coordinates. Make sure this is cell 2 and cell 1 dot row num. So if y diff is equals to 1, which means that we're checking for the bottom cell. So if we're checking for the bottom cell, that means cell 1 dot walls dot bottom wall is equals to false, and cell 2 dot walls dot top wall is equals to false. And if it's y diff of -1, that means we're checking the top cell. So in this case, we'll just swap out the walls. So we can just copy this and paste here, except we'll just make the cell 1 as cell 2 and cell 2 as cell 1. And that should be it. That will essentially help us in removing the wall between them. Okay. So we have removed the walls between this cell and the next cell. Next, what we're going to do is that we're going to set our current as the next. And then the same thing will happen with the next one. Oh yes, and another thing is that we're going to mark our next cell which we have chosen as visited as well. Because we have first of all taken our current cell, we have visited it, and we've set it to visited. Then we're going to select a random neighbor for that current cell. If that random neighbor is available, we're going to set that random number, a random cell, to be visited, and then we're going to push its parent node or the current cell into the stack so we can backtrack later on. And then we're going to remove the walls between both of those cells. And then we're going to set our current cell as the next cell, because this function will be called again and again. This function will essentially then check for the next cell, and it will apply the same procedure for the next one, and then the next, so on. But as I had mentioned, sometimes the neighbor won't be available. So in this case, if the next neighbor is not available, we're going to check else if stack.length is greater than 0. So if our stack has the length greater than 0, we can pop one of the nodes out of the stack as we had previously mentioned, and that will give us the parent node or the parent cell. So stack.pop will give us that cell, or will remove that first cell, and we're going to set our current cell to this cell. Now the last case will be if our stack is equals to 0, if our stack dot length is equals to 0, that means we don't have any more searching to do, and which also means that all of the nodes have been searched and the entire maze has been completely made. This means we can now return. And that should be it. We can now call this DFS maze over here, this .dfs maze. And you can see this in action. It's saying cannot read properties of undefined index.js89. 89, this dot row num equals to this dot rows. All right, it's this dot rows -1. And this dot columns as well -1. And you can now see how it's doing all of the backtracking, and also it's generating the maze. It's always starting from the top right, and it's carving its way inside. But currently it looks very ghostly. We are absolutely not understanding where is our pointer or the head of the maze generator moving. And it looks quite oblivious how we can understand how is the maze being formed. We can see how each of the cells are being carved over so that there are no empty cells being left. And essentially we are creating a maze from the top left corner as intended. Another thing to notice here is that it creates a maze which is solvable. Therefore, there can be many outputs to this maze. You can easily solve the maze and you can get the target cell over here, or you can set the target cell here. It can be any target position from the start to the end, but there will be one pathway to that target cell. That is the essence of DFS maze generation. So now to visualize what exactly is our maze generation doing in the background, let's add some colors to this thing. So in the this dot cell, we're going to define this dot color, which will be black. And we are going to go to our show this dot drawWalls, and we're going to check if this dot visited. So we are saying that if this cell is visited, then we're going to create a rectangle. First of all, we're going to go back to the context and we're going to set context.fill style. This is like setting the background of any of the elements in as you would with CSS, but in this case, it will be the fill style or the fill color. So we'll set the fill color to the color. In fact, we don't need to check for this dot visited. We can just do it directly. And I'll tell you why in a moment. We can do this dot fill style to color, and we can fill the rectangle over there. C dot fill rect. This will be the filling rectangle so that we can see what is exactly happening on each and every part of the cell, and we can see if that cell is visited or not, or if that cell is being backtracked. So C dot fill rect, we're going to pass into it the X and Y. Let's define the X and Y, or let's just do it column num multiply with the size, and then row num multiply with the size. That's the X and Y coordinate. Width will be the size and height will be the size. Currently, it is still black. Our walls have just thinned a little bit. And to mitigate that, we just need to add a little bit of offset to it because our rectangles are being formed, except that they're just overlapping the walls. So for that, we can just do a +1 offset to show off the walls. And for the size, we can reduce it by -2. Because our line width, if you remember, was -2. Right here in drawLine. Line width we have set to -2. Line width was set to 2. And we can see we have returned to the original width of the lines. They are now clear. Okay. Currently the color is black. So to now change the color, we will go to the next, and we're going to set that to, we can now set anywhere in the next condition. So we can set the current dot color is equals to green. Let us see what does that do. All right. And we can also set the other one to green. So for both of them, we can set it to green, and you can see now it's filling out all of these cells as it's going over them. Okay. Or in fact, let's just set this to black. The backtracking one can be set to black. Yes. So now you can see if we start again over here, that first of all, the green line is indicating the pathway taken for our DFS generation. You can see how the DFS generation takes one pathway in our maze, and then it backtracks along that path when it can't go any further. So the green cells over here indicating the actual stack or the actual path in this case, from where we can backtrack. And once our green line hits a corner, it starts backtracking all the way to the start. So always the start node will be our top left corner, and in backtracking, even the worst case scenario will be having the top left as our start node. Now we can see the current nodes, and we can also now see the nodes which are used in the backtracking. But yet we can't see the head of our actual maze generation. So where is exactly our maze generation in the maze right now? For that, we can create one small final function, which is highlight. A real easy function. We just need to copy this dot fill style and this dot and c dot fill rect from our show method and copy it here. But the c dot fill style will be set to red this time. The rest will remain the same. Now we just need to call our method. So we can now go to the DFS Maze method, and we can highlight our cell. current dot highlight. Copy that, and we'll also do that in the backtracking area. You should remember that this small else if is the important part in the DFS. This is the condition which handles the backtracking. So this if condition handles the forward movement of our DFS maze generator, and this else if condition handles the backtracking. So if we hit a corner node, or if we hit a node, or if we have reached the deepest part of our maze and we want to move backwards or backtrack from that position, this else if condition will handle that. So now we can see the head of our maze exactly. And now the fun thing over here is that we can extend our maze. We can extend it to 20, and it will create the maze. Similarly, we can also extend it to 30, and it will create a perfect maze. So this was our maze generated by our DFS maze generator. The last thing which we can try adding is that we have set that to green. All right. Okay, so there are no more bugs here. Yes, and it seems to work perfectly. So this was our maze generation. We can try out one last size. You can also, by the way, increase the size. So if I can increase this to 600, it will increase and will create a bigger maze. I can reduce this to 100 and it will still create a perfect maze, although it's a bit blurry. We'll just increase this to 600 and we can now add the rows and columns to be 50. And still it will create a perfect maze. So this was depth first search, randomized depth first search maze generation in HTML, CSS, and JavaScript. I hope you had enjoyed it. Leave a like and subscribe, and I'll see you in the next one.